The solar system's fastest winds blow on its coldest planet. Neptune sits almost 3 billion miles from our Sun, yet somehow this frozen world generates supersonic storms. Most people expect the outer solar system to be completely dead. Just cold, empty space where nothing ever happens. That assumption completely falls apart when you see what Neptune actually does. Tonight we're discovering how scientists first spotted these impossible storms. We'll uncover the mysterious power source driving all this violence. Before we dive into this frozen fury, drop a comment about where you're listening from. If you enjoy these cosmic explorations, consider subscribing. These journeys to the solar system's edge deserve to be shared. For decades, scientists expected Neptune to be completely quiet. The planet gets almost no warmth from our distant sun. Logic said any weather should be basically non-existent. A robot spacecraft called Voyager 2 shattered that assumption. In 1989, its cameras captured something nobody predicted. A massive dark hurricane dominated the planet's southern half. This storm system was bigger than our entire Earth. The structure looked familiar yet alien. Scientists recognized it as a hurricane, like the ones we get on Earth. But this storm appeared dark and menacing against Neptune's bright blue surface. The contrast made it look almost evil. This great dark spot spun counterclockwise in perfect atmospheric physics. Supersonic winds screamed around its edges faster than jet planes. Material spiraled inward through multiple layers of Neptune's thick atmosphere. Distance from the sun clearly doesn't guarantee calm weather. Here's what puzzled every scientist. Neptune actually produces more heat than it receives from the sun. The planet has its own internal heating system that nobody fully understands. This hidden furnace drives everything you see. Deep inside Neptune, the planet's own weight squeezes material so hard it generates tremendous heat. That energy creates massive rising columns of hot gas that travel thousands of miles upward. Neptune spins very fast, completing one day in just 16 hours. This rapid rotation transforms those rising heat columns into organized wind systems. The spinning motion sculpts them into high-speed atmospheric rivers. Without any solid ground to slow them down, these winds accelerate to incredible speeds. Neptune's fastest winds reach 1,200 miles per hour. That's faster than sound travels through Earth's air. Internal heating can create far more violent weather than sunlight alone. Something shocking happened between space missions. When Voyager discovered the Great Dark Spot in 1989, scientists assumed it would be permanent. Jupiter's Great Red Spot has raged for centuries. After all, the Hubble Space Telescope proved them spectacularly wrong. By the mid-1990s, astronomers looked for Neptune's famous storm. They found nothing. The massive hurricane had completely vanished. This disappearance revealed something important about planetary storms. Unlike Jupiter's long-lived weather systems, Neptune's storms can simply run out of energy. The Great Dark Spot gradually shrank as is mixed with surrounding atmosphere. Scientists watched the storm's boundaries become fuzzy and undefined. Its rotation weakened over several years. Eventually, the entire system dissolved into Neptune's general atmospheric circulation. Giant storms aren't necessarily permanent features of planetary atmospheres. Neptune didn't stay calm after losing its Great Dark Spot. The planet just reorganized its violent weather into different patterns. New storms began appearing in the northern hemisphere during the 2000s. These newer storm systems behave differently than their predecessor. Instead of one giant hurricane, Neptune now hosts multiple smaller storms that appear and disappear over several year cycles. Each one still dwarfs Earth's largest hurricanes. Scientists noticed these storms move around Neptune's surface more actively. They change latitude and longitude as they evolve. Some storms merge together while others split apart into separate systems. The variety of storm types surprises researchers. Some appear as dark ovals like the original Great Dark Spot. Others show up as bright white cloud systems. Each type seems to form under slightly different atmospheric conditions. Neptune's atmosphere continuously reorganizes itself into new patterns of violence. Neptune's brilliant blue color comes from methane gas in its atmosphere. This chemical absorbs red light from the sun while reflecting blue light back to space. The result creates one of the most beautiful colors in our solar system. The atmosphere consists mainly of hydrogen and helium, like other giant planets. But Neptune contains much more methane than Jupiter or Saturn. This methane creates unique cloud chemistry when it freezes in the planet's upper atmosphere. At Neptune's extreme distances, methane condenses into ice crystals that form high-altitude clouds. These clouds appear bright white against the planet's blue background. Solar radiation breaks down some methane into more complex chemicals called hydrocarbons. The atmospheric pressure increases dramatically toward Neptune's interior. What starts as gas near the surface eventually becomes liquid, then potentially solid material under crushing pressure. This exotic atmospheric chemistry creates cloud formations impossible anywhere else in our solar system. Neptune radiates 2.6 times more energy into space than it receives from the Sun. This energy budget defies expectations for such a distant, cold world. Something inside the planet generates tremendous amounts of heat. Scientists propose several possible heat sources. Gravitational compression from the planet's formation might still be releasing energy after billions of years. Helium rain could be falling through the interior, generating friction heat as it descends. Radioactive decay of elements in Neptune's core provides another potential energy source. The planet might also experience tidal heating from gravitational interactions with its moons. These internal processes could maintain heat production for astronomical timescales. This internal heating explains why Neptune has such violent weather despite receiving minimal solar energy. The planet essentially creates its own weather system from the inside out. Internal heat sources can sustain atmospheric activity far longer than stellar radiation alone. Neptune experiences the most extreme seasons in our solar system. Each season lasts approximately 40 Earth years because Neptune takes in 65 years to complete one orbit around the Sun. The planet's tilted axis creates dramatic seasonal changes in solar heating patterns. During Neptune's summer, one hemisphere receives continuous sunlight for decades. The winter hemisphere remains in comparative darkness for the same extended period. These long seasonal cycles influence Neptune's storm patterns over human timescales. Scientists have observed gradual changes in atmospheric circulation as the Plowly Moonet slowly moves through its orbital seasons. Current observations show Neptune's southern hemisphere transitioning from summer toward autumn. This seasonal shift might explain some of the changes in storm activity patterns observed over recent decades. Understanding Neptune's weather requires thinking in terms of centuries rather than years. Neptune remained a complete mystery until advanced technology reached the outer solar system. Ground-based telescopes could barely detect the planet as a tiny blue dot until the late 20th century. Voyager 2's 1989 flyby provided humanity's first detailed look at Neptune's atmosphere. The spacecraft's cameras revealed storm systems and atmospheric dynamics that nobody had imagined possible on such a distant world. The Hubble Space Telescope revolutionized Neptune studies by providing decades of continuous monitoring. This space-based observatory tracked the appearance and disappearance of major storm systems over multiple years. Modern ground-based telescopes use adaptive optics to compensate for Earth's atmospheric distortion. These systems now provide images of Neptune sharp enough to track individual cloud features and measure wind speeds. Future missions and advanced telescopes will continue revealing new secrets about this dynamic world's violent atmospheric behavior. Neptune breaks a fundamental rule of planetary science. Cold worlds shouldn't produce more energy than they receive. Yet this frozen giant radiates 2.6 times more heat into space than it gets from our distant sun. This energy imbalance creates one of astronomy's biggest puzzles. Most planets in our solar system either absorb solar energy or slowly cool down over time. Neptune stands out. The excess heat comes from deep within the planet's interior. Scientists call this internal energy generation, and it's been powering Neptune's violent weather for billions of years. Without this mysterious internal furnace, Neptune would be a completely dead, frozen world. This internal heating system explains why this distant cold planet hosts such violent atmospheric activity. Picture enormous columns of hot gas rising from Neptune's core toward its surface. These convection currents stretch through thousands of miles of dense atmosphere. They carry tremendous amounts of energy upward in a continuous cycle. The process works like a giant atmospheric conveyor belt. Hot material rises from deep inside the planet while cooler material sinks back down to replace it. This creates massive circulation patterns that dwarf anything happening on Earth. These rising heat columns provide the raw energy that powers Neptune's entire weather system. As they reach the upper atmosphere, they interact with the planet's rapid rotation to create organized wind patterns. Convection on this scale can only occur when a planet generates substantial internal heat. Neptune spins once every 16 hours, much faster than Earth's 24-hour day. This rapid rotation creates a powerful force that deflects moving air masses in predictable directions. Scientists call this the Coriolis effect. When rising heat columns encounter Neptune's spinning motion, they get twisted into spiral patterns. Instead of moving straight up, the hot air begins rotating as it rises. This transforms chaotic heat motion into organized atmospheric rivers. The faster a planet spins, the stronger this deflecting force becomes. Neptune's relatively quick rotation rate means its Coriolis effect can sculpt atmospheric motion into highly organized wind systems. Planetary rotation rate directly controls how atmospheric heat gets organized into wind patterns. Temperature differences across Neptune's atmosphere create zones of high and low pressure. These pressure variations act like atmospheric highways that channel air movement in specific directions. Air naturally flows from high-pressure areas toward low-pressure zones, just like water flowing downhill. The greater the pressure difference, the faster the air moves between these regions. Neptune's internal heating creates extreme temperature contrasts across different atmospheric regions. These temperature differences generate gradients steep enough to accelerate winds to supersonic velocities. Atmospheric pressure differences provide the driving force that pushes Neptune's winds faster than sound. A fundamental physics principle governs how rotating objects behave when their size changes. When spinning material contracts, it must spin faster to conserve what scientists call angular momentum. Think of an ice skater pulling their arms closer to their body during a spin. As their mass moves inward, their rotation rate increases dramatically. The same physics applies to Neptune's atmospheric circulation. When air masses in Neptune's atmosphere get compressed by pressure changes, they start rotating faster. This compression happens naturally as atmospheric material moves between different pressure zones. Conservation of angular momentum explains why Neptune's winds accelerate beyond what pressure alone could achieve. Neptune's atmosphere organizes itself into distinct bands of high-speed winds running parallel to the planet's equator. These atmospheric rivers, called jet streams, maintain consistent speeds across vast distances. Temperature differences between Neptune's equator and poles drive the formation of these wind bands. Warm equatorial air rises while cooler polar air sinks, creating circulation cells that get organized by the planet's rotation. Each jet stream represents a balance between heating patterns, pressure gradients, and rotational forces. Once established, these wind bands can persist for decades or longer. Jet stream formation requires the right combination of internal heating and planetary rotation. Neptune's atmosphere becomes unstable when temperature changes occur at different altitudes. This creates a condition scientists call baroclinic instability, where vertical temperature structures enhance horizontal wind motion. When warm air sits below cold air at the same atmospheric level, the system becomes dynamically unstable. Small disturbances get amplified as the atmosphere tries to restore balance between these temperature layers. This instability acts like an atmospheric amplifier that takes modest wind speeds and increases them dramatically. The process feeds on the temperature contrasts created by Neptune's internal heating. Atmospheric instability can transform moderate winds into supersonic jet streams. Neptune's atmosphere contains motion at every possible scale, from tiny eddies to planet-spanning wind systems. These different-sized motions constantly interact and exchange energy with each other. Large-scale wind patterns break down into smaller rotating features, while small disturbances can grow into major atmospheric systems. This energy transfer process, called turbulent cascade, efficiently distributes power throughout the entire atmospheric system. The cascade effect means energy from Neptune's internal heating gets spread across all atmospheric scales. This creates a complex web of interacting motions that sustains the planet's violent weather patterns. Turbulent energy transfer maintains atmospheric activity across all size scales simultaneously. Neptune lacks the solid surface that slows down winds on rocky planets like Earth. Without mountains, valleys, or ground friction, atmospheric motion encounters almost no resistance from below. On Earth, surface features create drag that limits maximum wind speeds. Trees, buildings, and terrain irregularities all slow down moving air masses through friction. Neptune's atmosphere extends all the way down to a liquid or slushy interior with no solid boundaries. This means wind systems can accelerate to their theoretical maximum speeds without interference. The absence of surface friction removes the primary speed limit on atmospheric motion. Different layers of Neptune's atmosphere have dramatically different densities. These density variations create powerful buoyancy forces that drive vertical atmospheric motion and enhance wind generation. When less dense material sits below denser material, the atmosphere becomes unstable. The lighter material wants to rise while the heavier material wants to sink, creating strong vertical currents. These density-driven motions add another layer of complexity to Neptune's atmospheric dynamics. They interact with temperature-driven convection and rotation-induced wind patterns to create an incredibly active weather system. Atmospheric density differences provide additional energy sources that sustain Neptune's violent wind systems. Scientists expected Neptune's Great Dark Spot to last for centuries. Jupiter's famous Great Red Spot has been raging for hundreds of years. Logic suggested Neptune's massive hurricane would behave the same way. The Hubble Space Telescope shattered that assumption in the mid-1990s. Astronomers pointed the orbiting observatory toward Neptune, expecting to photograph the famous storm system. Instead, they found completely empty space. The Great Dark Spot had vanished without a trace. This Earth-sized hurricane simply disappeared after existing for at least several years. No planetary scientist had predicted such a rapid disappearance. Hubble's observations proved that giant planetary storms can be surprisingly temporary features. What kills a storm the size of Earth? The answer lies in energy supply and demand. Every hurricane needs continuous energy input to maintain its structure and rotation. Neptune's Great Dark Spot began losing power when its energy sources couldn't keep up with energy losses. Storms constantly lose energy through friction, heat radiation, and atmospheric mixing. Without adequate energy replacement, they inevitably weaken. The storm's energy came from temperature differences in Neptune's atmosphere. As these temperature contrasts gradually decreased, the storm had less fuel to maintain its violent rotation. Atmospheric storms require constant energy input to survive against natural energy loss processes. Telescopic observations revealed exactly how the Great Dark Spot died. The storm's boundaries began contracting inward like a deflating balloon. Each year, the hurricane's diameter grew smaller. Astronomers measured the storm's shrinking rate by comparing images taken months apart. The dark oval gradually lost its distinct shape as its edges became less defined. What started as a sharp-edged hurricane became an increasingly fuzzy atmospheric disturbance. This shrinking process took several years to complete. Scientists watched the storm lose structural integrity as it contracted toward its center. Eventually, the entire system became too small to maintain organized rotation. Storm death occurs through gradual boundary contraction rather than sudden collapse. The Great Dark Spot's edges began mixing with surrounding atmospheric gases. This mixing process gradually erased the sharp boundary between storm air and normal atmospheric circulation. Think of dropping food coloring into water. Initially, the color remains distinct and separate. Over time, molecular motion spreads the color until it becomes indistinguishable from the surrounding water. Neptune's atmospheric turbulence created similar mixing between the storm and its environment. Small-scale eddies and wind shears gradually transported storm material into the surrounding atmosphere. This process weakened the storm's identity as a separate weather system. Atmospheric mixing can dissolve even the largest storm systems through boundary erosion. The Great Dark Spot didn't disappear all at once. Instead, it fell apart in stages, starting from Neptune's upper atmospheric layers and working downward. Scientists observed the storm's upper portions losing organization first. High-altitude winds disrupted the storm's vertical structure, breaking up the organized rotation that extended through multiple atmospheric levels. This top-down destruction process resembles how tall buildings collapse during demolition. The upper floors lose structural integrity first, and the collapse progresses downward through lower levels. Neptune's storm experienced similar layer-by-layer disintegration. Atmospheric storms maintain three-dimensional structure, and disruption at any level can trigger total system failure. Temperature differences provide the fundamental energy source for all atmospheric storms. The Great Dark Spot depended on temperature contrasts between its center and surrounding areas to maintain rotation. Over time, atmospheric mixing reduced these crucial temperature differences. Heat transfer gradually eliminated the thermal gradients that had powered the storm's circulation. Without temperature contrasts, the storm lost its primary energy source. This temperature balancing process, called thermal equilibration, occurs naturally in all fluid systems. Hot and cold regions eventually reach the same temperature through heat transfer. Once this happens, circulation stops. Storm systems die when thermal equilibration eliminates their temperature-driven energy source. Rotating storms gradually lose their spin energy through natural friction processes. The Great Dark Spot experienced internal friction as different parts of the storm rotated at slightly different speeds. This internal friction converts rotational energy into heat, which then radiates away into space. Scientists call this process angular momentum dissipation, and it affects all rotating systems in the universe. Atmospheric turbulence within the storm accelerated this energy loss process. Small-scale chaotic motions extracted energy from the large-scale rotation, gradually slowing the entire system. Rotational energy naturally dissipates through friction, causing all spinning systems to eventually slow down. Neptune's Great Dark Spot extended vertically through multiple atmospheric layers. Each layer rotated in coordination with the others, creating a coherent three-dimensional storm structure. Atmospheric disturbances began disrupting this vertical coordination. When different layers stopped rotating together, the storm lost its structural integrity. The organized hurricane became a collection of disconnected atmospheric motions. This vertical breakdown resembles what happens when a marching band loses its rhythm. Individual musicians continue playing, but the coordinated performance falls apart. Similarly, individual atmospheric motions continued, but organized storm behavior disappeared. Three-dimensional storm systems require vertical coordination to maintain their structure. The Great Dark Spot existed within a specific pattern of atmospheric wind flows. These surrounding winds, called jet streams, provided environmental support that helped maintain the storm's structure. Over time, Neptune's jet stream patterns shifted slightly. These changes altered the atmospheric environment around the storm, removing the conditions necessary for its continued existence. Weather systems on all planets depend on their atmospheric environment for survival. When background wind patterns change, even massive storms can lose their environmental support structure. Storms require compatible environmental conditions to survive long-term. Neptune's magnetic field may have undergone gradual changes that indirectly affected atmospheric circulation patterns. While magnetic fields don't directly control weather, they can influence the motion of charged particles in planetary atmospheres. These electromagnetic effects may create subtle changes in atmospheric electrical properties. Over long periods, such changes could modify atmospheric circulation patterns and storm behavior. The magnetic field influence may have been one of many factors that contributed to the Great Dark Spot's eventual demise. No single cause destroyed the storm. Instead, multiple processes combined to eliminate this massive weather system. Planetary magnetic field variations may indirectly influence atmospheric storm systems over extended time periods. Neptune refused to stay calm after losing its famous Great Dark Spot. Instead of becoming meteorologically quiet, the planet simply reorganized its violent weather into entirely new patterns. Astronomers discovered fresh storm systems emerging in Neptune's northern hemisphere during the 2000s. These new atmospheric disturbances appeared in regions that had shown little previous activity. The planet was essentially reinventing its weather from scratch. These northern storms displayed different characteristics than their southern predecessor. They formed in atmospheric conditions that hadn't supported major weather systems before. This proved that Neptune's atmosphere can generate storms in many different regions given the right circumstances. Planetary atmospheres can continuously create new weather patterns even after losing major storm systems. Instead of concentrating all its atmospheric energy into one massive hurricane, Neptune adopted a completely different approach. The planet began hosting multiple smaller storms simultaneously across various regions. These distributed storm systems operate like a network of interconnected weather factories. Each individual storm remains smaller than the original Great Dark Spot, but collectively they represent comparable atmospheric activity levels. Multiple smaller storms provide certain advantages over single large systems. They can cover more of the planet's surface and respond more quickly to changing atmospheric conditions. This distributed approach appears more dynamically stable. Multiple smaller storms can achieve the same total atmospheric activity as a single large storm while providing greater flexibility. Something visually striking accompanies Neptune's new dark storms. Brilliant white methane clouds form around the edges of these darker atmospheric systems, creating dramatic color contrasts. These bright companion clouds consist of methane gas that has frozen into ice crystals at high altitude. The chemical process occurs when storm systems lift methane-rich air into Neptune's extremely cold upper atmosphere. The resulting visual effect resembles dark storm centers, surrounded by gleaming white halos. This creates some of the most photogenic weather phenomena in the entire solar system. The contrast makes Neptune's storms easier to detect and study. Storm-driven atmospheric lifting can create spectacular cloud formations that enhance visual storm detection. Neptune's new storm systems refuse to stay in one place. Unlike Earth's hurricanes that follow predictable paths, Neptune's storms wander freely across the planet's surface in seemingly random directions. These wandering storms can change both latitude and longitude as they evolve. Some drift toward the poles while others migrate toward the equator. Certain storms even reverse direction during their lifetimes. This extreme mobility results from Neptune's complex atmospheric circulation patterns. Multiple competing wind systems can capture and redirect storms in various directions. The lack of solid surface features means nothing prevents this atmospheric wandering. Atmospheric storms on gas giant planets can exhibit extreme mobility patterns impossible on rocky worlds. Neptune's atmosphere follows a surprisingly regular schedule for creating and destroying storm systems. New storms appear roughly every few years, while existing ones dissipate on similar timescales. This cyclical behavior suggests that Neptune's atmospheric energy follows predictable patterns. The planet appears to cycle through periods of storm formation, followed by periods of storm dissipation. Scientists can now anticipate when new weather systems might emerge. These cycles likely reflect larger-scale changes in Neptune's atmospheric circulation. Energy builds up in certain regions until conditions become right for storm formation. Then the process repeats. Atmospheric energy accumulation and release can create predictable storm formation cycles on giant planets. Neptune's current storm population includes an enormous range of sizes. The smallest detectable systems span only a few hundred miles, while the largest approach the dimensions of entire Earth continents. This size diversity reflects different formation mechanisms operating simultaneously. Small storms form from local atmospheric instabilities, while large systems require planet-wide circulation changes. Each size category follows different physical rules. The variety of storm sizes means Neptune's atmosphere can respond to disturbances at multiple scales. Local temperature changes might create small storms, while global circulation shifts generate massive weather systems. Multi-scale storm formation allows planetary atmospheres to respond to disturbances across a wide range of energy levels. Neptune's storms display a surprising range of colors, from dark gray to bright white. These color differences reveal important information about storm composition, altitude, and atmospheric chemistry. Dark storms typically form deeper in the atmosphere, where they interact with different chemical compounds. Bright storms usually occur at higher altitudes, where methane ice crystals create reflective cloud surfaces. The color variations also indicate different formation processes. Some storms develop from rising deep atmospheric material, while others form from cooling upper atmosphere gases. Each type creates distinct visual signatures. Storm coloration provides diagnostic information about atmospheric composition and formation altitude. Neptune hosts storms that can rotate in both directions. Some systems spin clockwise while others turn counterclockwise, creating a complex pattern of atmospheric circulation across the planet. This rotational diversity depends on local atmospheric conditions where each storm forms. High-pressure and low-pressure regions naturally create opposite rotation directions. Neptune's atmosphere contains both types of pressure systems. The coexistence of opposite rotating storms creates interesting interaction dynamics. When storms with different rotation directions encounter each other, they can merge, cancel out, or create entirely new circulation patterns. Atmospheric pressure variations can generate storms with opposite rotation directions within the same planetary atmosphere. Neptune's multiple storms don't exist in isolation. They constantly interact with each other through atmospheric forces that can dramatically alter storm behavior and structure. When two storms approach each other, several outcomes become possible. They might merge into a larger system, circle around each other for a time, or split into multiple smaller storms. These storm interactions create some of the most complex atmospheric dynamics in the solar system. The resulting behavior patterns help scientists understand how atmospheric systems organize themselves on planetary scales. Multiple storm systems can exhibit complex interaction dynamics. Neptune's storm patterns may connect to the planet's incredibly long seasonal cycles. Each season on Neptune lasts roughly 40 Earth years because of the planet's distant orbit around the Sun. Recent observations suggest storm activity levels change as Neptune slowly transitions between seasons. The planet's southern hemisphere has been experiencing summer, which might explain increased storm formation rates. These seasonal connections mean Neptune's weather operates on multiple timescales simultaneously. Short-term storm cycles occur within longer seasonal patterns that span human generations. Planetary seasonal cycles can influence storm formation patterns across timescales much longer than individual weather systems. Why does Neptune appear brilliant blue while other giant planets look pale yellow or brown? The answer lies in a specific chemical process happening throughout Neptune's atmosphere. Methane gas molecules floating in Neptune's atmosphere absorb red light from the Sun while reflecting blue light back into space. This selective light absorption works like a cosmic color filter that removes red wavelengths from sunlight. The chemical process occurs when sunlight hits methane molecules in the upper atmosphere. These molecules preferentially absorb longer wavelengths, particularly red and orange light. Only shorter blue wavelengths escape back to space, creating Neptune's distinctive coloration. Atmospheric methane concentration helps control the intensity of blue coloration on giant planets. Neptune's extreme distance from the Sun creates conditions where methane gas actually freezes solid in the planet's upper atmosphere. This freezing process produces some of the most spectacular cloud formations in the solar system. At the frigid temperatures found high above Neptune's surface, methane transitions from gas to solid ice crystals. These methane ice particles reflect sunlight brilliantly, creating bright white clouds that contrast dramatically with the planet's blue background. The condensation process works exactly like water vapor forming clouds on Earth, except Neptune uses methane instead of water. When methane-rich air rises into the cold upper atmosphere, temperature drops trigger crystallization. Methane condensation creates highly reflective ice crystal clouds at specific atmospheric altitudes. Neptune shares the same basic atmospheric ingredients as Jupiter and Saturn. The vast majority of its atmosphere consists of hydrogen and helium gases, the two lightest elements in the universe. These primary atmospheric components reflect Neptune's formation process billions of years ago. When the planet formed, it captured massive amounts of hydrogen and helium directly from the early solar system's gas and dust disk. Hydrogen makes up roughly 80% of Neptune's atmosphere, while helium accounts for most of the remainder. These percentages broadly match the chemical composition of the Sun and other stars throughout the universe. Giant planet atmospheres preserve the original chemical composition of the solar system's formation materials. Something's missing from Neptune's upper atmosphere that dominates Jupiter's weather systems. Ammonia, which helps create Jupiter's colorful cloud bands, remains trapped deep within Neptune's interior. The temperature difference explains this atmospheric chemistry puzzle. Jupiter's warmer conditions allow ammonia to rise through the atmosphere and form visible clouds. Neptune's extreme cold forces ammonia to freeze solid before reaching observable atmospheric levels. This frozen ammonia gets locked away in Neptune's deep interior, unable to participate in upper atmospheric chemistry. Only trace amounts ever reach the regions where instruments can detect them. Temperature conditions determine which chemicals can participate in observable atmospheric processes. Ultraviolet radiation from the sun triggers complex chemical reactions in Neptune's atmosphere. These high-energy light rays break apart methane molecules and reassemble them into entirely different chemical compounds. The process creates hydrocarbon molecules like ethane and acetylene through photochemical reactions. Scientists call this process photochemistry because light energy drives the chemical transformations. These newly formed hydrocarbon molecules have different properties than the original methane. Some condense into particles while others remain gaseous. The variety of hydrocarbon compounds adds chemical complexity to Neptune's atmospheric composition. Solar ultraviolet radiation can drive complex atmospheric chemistry through photochemical decomposition processes. Neptune's atmosphere organizes itself into distinct cloud layers at different altitudes. Each layer contains clouds made from different chemical compounds that condense at specific temperatures and pressures. Lower altitude clouds form from substances that condense at warmer temperatures. Higher altitude clouds consist of chemicals that only freeze under extreme cold conditions. This creates a stratified system where cloud composition changes with height. The layered structure resembles a multi-story atmospheric building. Each floor hosts different chemical processes and cloud types. Instruments can detect these distinct layers through spectral analysis. Atmospheric temperature gradients create vertically organized cloud systems with altitude-dependent chemical composition. Photochemical reactions in Neptune's atmosphere produce tiny particles that create a persistent atmospheric haze. These microscopic particles form when ultraviolet sunlight breaks down atmospheric gases into reactive fragments. The resulting haze particles scatter light in ways that affect atmospheric visibility and optical properties. This photochemical smog resembles pollution haze in Earth's cities, except it forms through natural space chemistry processes. These haze particles can grow large enough to affect how light travels through Neptune's atmosphere. They contribute to the planet's overall optical properties and influence how we observe surface features. Atmospheric photochemistry can produce particle haze that affects planetary optical properties and visibility. Atmospheric pressure on Neptune increases dramatically with depth, creating conditions that transform familiar substances into exotic physical states. These extreme pressures crush atmospheric gases into forms that don't exist anywhere on Earth. Deep within Neptune's atmosphere, pressure becomes so intense that hydrogen and helium behavior changes completely. What starts as normal gas in the upper atmosphere transitions into liquid, then potentially solid phases under crushing compression. These pressure-induced phase transitions create regions where the same chemical substance exists in multiple physical states simultaneously. The boundaries between gas, liquid, and solid become blurred under extreme conditions. Extreme atmospheric pressure can force chemical substances through multiple phase transitions within the same planetary atmosphere. Something unusual happens in certain regions of Neptune's atmosphere where temperature actually increases with altitude. This temperature inversion defies normal atmospheric behavior, where upper layers should be colder. These inverted temperature layers suppress normal atmospheric mixing and convection. When upper air becomes warmer than lower air, the natural tendency for hot air to rise gets eliminated. The temperature inversions create stable atmospheric layers that resist vertical mixing. This can trap chemical compounds at specific altitudes and create distinct atmospheric zones with different properties. Temperature inversions can create stable atmospheric stratification that suppresses normal convective mixing processes. The ratio of different atomic varieties, called isotopes, in Neptune's atmosphere provides clues about how and where the planet formed billions of years ago. These chemical fingerprints preserve information about the early solar system. Scientists analyze the abundance of heavy hydrogen and different helium varieties to understand Neptune's origin story. The specific isotope ratios reflect the temperature and chemical conditions present during planetary formation. These isotopic signatures differ from what scientists observe in the inner solar system, suggesting Neptune formed under different conditions or migrated from its original formation location. Atmospheric isotope ratios preserve chemical evidence of planetary formation conditions and evolutionary history. Neptune has an energy paradox that puzzles scientists. Distant worlds usually radiate little heat from sunlight alone, yet Neptune produces 2.6 times more heat than it gets from our Sun. This energy excess puzzles scientists because it suggests Neptune has its own internal power source. Most planets either absorb solar energy or gradually cool down over billions of years. Neptune does neither. The extra heat emerges from somewhere deep within the planet's interior. Scientists call this phenomenon internal heat generation, and it's been powering Neptune's atmospheric violence for eons. Internal energy sources can make distant planets far more active than their solar heating alone would permit. Gravity never stops working on Neptune. The planet's enormous mass constantly pulls inward on itself, causing the entire world to slowly shrink over geological timescales. This gravitational contraction converts motion energy into heat through a process scientists call gravitational heating. As material falls inward under its own weight, the motion energy transforms into thermal energy. The contraction happens incredibly slowly by human standards, but generates substantial heat over millions of years. Even tiny amounts of shrinkage across such enormous masses can produce planet-warming energy levels. Gravitational self-compression can sustain internal heating for billions of years on massive planets. Something unusual might be falling inside Neptune's atmosphere like rain, except this rain consists of helium-rich droplets. This helium rain could generate substantial internal heat through friction. The process begins when helium separates from hydrogen in Neptune's interior due to pressure and temperature conditions. The separated helium becomes denser and begins falling toward the planet's core like metallic rain. As these droplets fall through thousands of miles of dense material, friction converts their motion into heat energy. This process could operate continuously for billions of years, providing ongoing internal heating. Atmospheric helium separation can create internal heating through gravitational settling and friction processes. Neptune likely contains radioactive elements that naturally break down over time, releasing energy through atomic decay processes. These radioactive materials act like tiny nuclear reactors scattered through the planet's deeper interior. Radioactive decay produces heat when unstable atomic nuclei spontaneously transform into more stable foams. This process releases energy that accumulates as heat within the planetary interior. Elements like uranium, thorium, and potassium undergo radioactive decay continuously. Even small concentrations of these materials can generate significant heat when distributed through a planet-sized mass. Radioactive decay provides a reliable long-term heat source that operates independently of external energy inputs. Neptune's moons exert gravitational forces that can slightly deform the planet's shape. These tidal forces may create internal friction as different parts of Neptune get stretched and compressed. The largest moon, Triton, orbits in an unusual backward direction that may enhance these tidal effects. This retrograde orbit can create stronger gravitational interactions than many normal moon systems. Tidal heating works like repeatedly flexing a piece of metal until it becomes hot. The constant gravitational kneading converts mechanical energy into thermal energy throughout Neptune's interior. Gravitational interactions with orbiting moons may contribute some internal heating through tidal deformation processes. Materials inside Neptune undergo phase transitions as pressure and temperature conditions change with depth. These phase changes release stored energy in the form of latent heat. When substances transition from gas to liquid or liquid to solid, they release energy that had been stored in their molecular bonds. This latent heat contributes additional thermal energy to Neptune's interior heating budget. The phase transitions occur continuously as convection circulates material between different pressure and temperature zones. Each transition cycle releases another burst of latent heat energy. Phase change processes can provide supplementary heating through latent heat release during material state transitions. Neptune's interior operates like a giant thermal conveyor belt that efficiently transports heat from the deep interior to the atmosphere. This convection system helps internal heat reach levels where it can power atmospheric activity. Hot material rises from deep within the planet, while cooler material sinks back down to replace it. This creates circulation patterns that carry thermal energy upward through thousands of miles of planetary interior. Convective heat transfer works much more efficiently than simple heat conduction. Without convection, Neptune's internal heat would remain trapped in the deep interior instead of powering surface weather systems. Efficient convective circulation can transport internal planetary heat to atmospheric levels where it drives weather activity. Neptune's thick interior acts like a massive thermal blanket that prevents heat from escaping quickly. This thermal insulation allows internal heat to accumulate over geological timescales. Heat moves very slowly through solid and liquid materials compared to how quickly it moves through gases. Neptune's dense interior creates thermal barriers that trap heat for millions of years. This insulation effect means heat generated during Neptune's formation billions of years ago might still be slowly working its way toward the surface. The planet essentially stores thermal energy for extended periods. Poor thermal conductivity in planetary interiors can trap and store internal heat for geological timescales. Neptune's changing magnetic field may create electrical currents within parts of the planet's conducting interior. These electrical currents can generate resistance heating similar to how electric stoves produce heat. The magnetic field changes as Neptune rotates and as its internal circulation patterns evolve. These magnetic field variations can induce electrical currents in conducting materials within the planet. Electrical resistance converts current flow into thermal energy through electromagnetic heating processes. This provides another potential source of internal heat generation within Neptune's interior. Magnetic field variations may generate some internal heating through electrical resistance in planetary conducting materials. Neptune still retains heat from the violent processes that created it billions of years ago. The energy from countless collisions during planetary formation created enormous amounts of heat that Neptune continues to slowly release. During Neptune's formation, asteroids, comets, and other debris constantly bombarded the growing planet. Each impact converted motion energy into heat energy that accumulated within the planetary interior. This primordial heat represents stored energy from the solar system's chaotic early history. Neptune's massive size and poor thermal conductivity allow it to retain this formation heat over astronomical timescales. Planetary formation energy can remain stored within massive worlds for billions of years after initial accretion processes. Imagine winter lasting your entire lifetime, then continuing for your children's lifetimes too. Neptune experiences seasonal changes on a scale that dwarfs anything possible on Earth. Each season on Neptune lasts around 40 Earth years. This means a single Neptunian winter spans multiple human generations. People are born, live their entire lives, and die within a single season on this distant world. The extreme seasonal duration results from Neptune's enormous orbital distance from the Sun. The planet takes 165 Earth years to complete one trip around our star. This creates seasonal timescales that exceed recorded human history. Planetary orbital periods directly determine seasonal duration on worlds in the solar system. Neptune's rotational axis tilts at roughly the same angle as Earth's. However, this tilt creates far more extreme seasonal effects because of Neptune's vast distance from the Sun. During Neptune's summer, one hemisphere receives continuous sunlight for decades while the opposite hemisphere remains in comparative winter darkness. The tilted axis means polar regions can receive more total solar radiation than equatorial zones. This axial tilt effect gets amplified by Neptune's orbital distance. Even small changes in solar angle create dramatic differences in heating patterns across the planet's atmosphere over multi-decade timescales. Axial tilt effects become more pronounced on planets with longer orbital periods around their stars. Temperature differences between Neptune's summer and winter hemispheres create enormous atmospheric circulation patterns. These hemisphere-scale temperature contrasts drive weather systems larger than anything seen on inner planets. The summer hemisphere becomes significantly warmer than the winter hemisphere over decades-long periods. This temperature difference creates pressure gradients that span the entire planet and drive massive atmospheric circulation. Heat transfer between hemispheres occurs through atmospheric circulation patterns that can persist for years. The planet's atmosphere acts like a giant heat distribution system working to balance these extreme temperature differences. Large-scale temperature contrasts drive atmospheric circulation patterns that operate on planetary scales. Something counterintuitive happens during Neptune's summer season. The polar regions can actually receive more solar energy than areas near the equator, creating an inverted heating pattern. This polar heating paradox occurs because Neptune's tilted axis allows summer polar regions to face the Sun continuously for decades. Meanwhile, equatorial regions experience day-night cycles that reduce their total solar energy input. The result creates temperature patterns opposite to what we experience on Earth. Neptune's summer pole can become one of the warmest places on the planet, while the equator remains relatively cool. Extreme axial tilt can create inverted temperature patterns where poles receive more heating than equatorial regions. Neptune's atmospheric circulation completely reorganizes itself as seasons change over multi-decade periods. Wind patterns that flow in one direction during summer can reverse during winter. These circulation changes occur because seasonal heating patterns determine where hot air rises and where cold air sinks. As the heated hemisphere changes, the entire atmospheric circulation system must reorganize accordingly. The transition between circulation patterns takes years to complete. During these transition periods, Neptune's atmosphere exhibits complex mixing between old and new circulation patterns. Seasonal heating changes can trigger complete reorganization of planetary atmospheric circulation systems. Neptune's high-speed wind bands, called jet streams, slowly migrate to different latitudes as seasons progress. These atmospheric highways can shift their positions over decades-long timescales. Jet stream migration occurs because seasonal temperature changes alter the atmospheric pressure patterns that control where these high-speed winds form. As heating patterns shift, the jet streams follow. This jet stream movement affects storm formation and atmospheric mixing patterns across the entire planet. Weather systems that form in one latitude during summer might form elsewhere during winter. Seasonal temperature changes can cause high-altitude wind systems to migrate across different planetary latitudes. Neptune's storm formation follows seasonal patterns linked to the planet's position in its orbital cycle. certain seasons appear more favorable for generating major atmospheric disturbances. Scientists have observed correlations between orbital position and storm activity levels. The planet currently experiences increased storm activity as its southern hemisphere progresses through summer conditions. These seasonal storm patterns suggest that long-term solar heating changes influence atmospheric instability. Decades of heating build up atmospheric energy that eventually gets released through storm formation. Seasonal energy accumulation can create cyclical patterns in planetary storm formation activity. Cloud formation patterns on Neptune shift dramatically between seasons as temperature and circulation changes affect where atmospheric moisture condenses into visible clouds. Summer hemispheres tend to produce more high-altitude clouds as increased heating drives more atmospheric convection. Winter hemispheres show fewer clouds as reduced heating limits atmospheric moisture transport. These cloud pattern changes alter Neptune's overall appearance when viewed through telescopes. The planet's visible features migrate and transform as seasonal effects redistribute atmospheric activity. Seasonal atmospheric changes can cause large-scale redistribution of visible cloud formation patterns. Neptune's massive atmosphere responds slowly to seasonal changes, creating a thermal lag effect where atmospheric temperatures take years to adjust to new heating patterns. This delayed response occurs because Neptune's thick atmosphere acts like a giant thermal mass that resists rapid temperature changes. The atmosphere must gradually adjust to new equilibrium conditions over multi-year timescales. Thermal lag means Neptune's atmospheric temperature patterns lag behind its orbital position by several years. Maximum seasonal heating effects do not appear until years after the astronomical seasonal change occurs. Massive planetary atmospheres exhibit thermal inertia that delays their response to seasonal heating changes. Understanding Neptune's current atmospheric state requires considering seasonal effects that will unfold over the next several decades. Today's storm patterns influence atmospheric conditions that will not fully develop for years. Neptune's southern hemisphere currently experiences summer conditions that will continue for another decade. This ongoing seasonal heating may drive increased storm activity and circulation changes throughout this period. These long-term atmospheric trends allow scientists to make predictions about Neptune's future weather patterns with unusual confidence. The planet's seasonal timescales exceed human planning horizons, but provide predictable long-term patterns. Extreme seasonal timescales can make long-term atmospheric prediction more reliable than short-term weather forecasting. For over a century, Neptune remained a complete mystery to human science. Ground-based telescopes could barely detect it as a tiny blue dot in their most powerful instruments. Everything changed with a single robotic mission. Voyager 2 became the first and only spacecraft to visit Neptune when it flew past the planet in 1989. This robotic explorer carried sophisticated cameras and instruments that could observe atmospheric details impossible to see from Earth. The spacecraft's close-up observations revealed Neptune's violent storm systems for the first time in human history. Images showed the Great Dark Spot, supersonic winds, and complex atmospheric dynamics that nobody had imagined. Direct spacecraft observation provided the first detailed view of Neptune's true atmospheric behavior and complexity. The Hubble Space Telescope revolutionized Neptune science by providing something no ground-based observatory could offer: decades of continuous high-quality observations from above Earth's interfering atmosphere. Hubble's position in space eliminates atmospheric distortion that blurs ground-based telescope images. This allows the Space Telescope to track individual storm systems and atmospheric features over year-to-year timescales. The telescope's long operational lifetime enabled scientists to watch the Great Dark Spot disappear and new storms emerge. These multi-decade observations revealed that Neptune's atmosphere changes far more rapidly than anyone expected. Long-term space-based monitoring can reveal atmospheric evolution patterns invisible to short-term observation campaigns. Earth's atmosphere constantly wobbles and distorts light from distant objects, making ground-based telescope images fuzzy and unclear. A revolutionary technology called adaptive optics solved this fundamental problem. Adaptive optics systems use computer-controlled mirrors that flex hundreds of times per second to cancel out atmospheric distortion. These flexible mirrors essentially create artificial stars in Earth's atmosphere to measure and correct the wobbling effect. This technology allows ground-based telescopes to achieve image sharpness rivaling space telescopes at a fraction of the cost. Modern adaptive optics can track individual cloud features on Neptune from Earth's surface. Real-time atmospheric correction technology enables ground-based telescopes to achieve space-quality image resolution. Visible light only shows Neptune's surface cloud layers. Scientists needed to see deeper into the planet's atmosphere to understand the heat sources driving its violent weather systems. Infrared telescopes detect heat radiation instead of visible light. This thermal vision technique allows astronomers to map temperature differences throughout Neptune's atmospheric layers and measure internal heat emission. Infrared observations revealed that Neptune radiates more heat than it receives from the sun. They also showed hot spots associated with storm systems and circulation patterns invisible to normal optical telescopes. Thermal infrared observation can penetrate atmospheric layers to reveal internal heat sources and temperature distribution patterns. How can scientists determine what chemicals exist in Neptune's atmosphere without physically traveling there? The answer lies in analyzing the specific colors of light that Neptune reflects and emits. Spectroscopy breaks down light into its component colors like a prism creating a rainbow. Different chemical compounds absorb and emit specific colors, creating unique fingerprints that identify their presence. This technique revealed methane, hydrogen, helium, and trace chemicals in Neptune's atmosphere. Spectral analysis also measures wind speeds by detecting how atmospheric motion shifts the colors of reflected sunlight. Spectroscopic light analysis enables remote chemical identification and motion measurement across interplanetary distances. Modern supercomputers can simulate Neptune's entire atmospheric system using mathematical equations that describe fluid motion, heat transfer, and chemical processes. These computer models create virtual Neptunes where scientists can test theories about storm formation, wind generation, and atmospheric circulation. The simulations can run thousands of times faster than real atmospheric processes. Computational modeling helps explain observations that would otherwise remain mysterious. Models can predict how atmospheric changes might evolve and test what would happen under different heating or rotation conditions. Computer simulation enables controlled experimentation on planetary atmospheric systems impossible to study through observation alone. Neptune observation requires coordinating telescopes around the world to provide continuous coverage as Earth rotates. International scientific cooperation makes this global coordination possible. When Neptune sets below the horizon at one observatory, telescopes on other continents can continue observations. This creates 24-hour monitoring capabilities that no single telescope facility could achieve alone. Coordinated observations also provide multiple independent measurements that improve data reliability. Different telescopes and instruments can cross-check each other's results to ensure accuracy. International telescope coordination enables continuous planetary monitoring and enhanced measurement reliability through global scientific cooperation. Advanced camera technology and computer processing have revolutionized amateur astronomy. Dedicated amateur astronomers now contribute meaningful observations of Neptune using equipment available to private individuals. Modern amateur telescopes equipped with sensitive digital cameras can track atmospheric changes and occasionally detect new storm systems. Computer image processing allows amateurs to enhance their observations to professional quality standards. Amateur astronomers provide valuable long-term monitoring that supplements professional observations. Their consistent nightly observations can catch rapid changes that scheduled professional telescope time might miss. Technological advancement has democratized planetary observation by enabling amateur astronomers to contribute scientifically valuable data. The James Webb Space Telescope and planned future space missions will provide unprecedented capabilities for studying Neptune's atmospheric behavior with revolutionary precision and detail. Webb's enormous mirror and advanced infrared instruments can detect atmospheric features and chemical processes invisible to current telescopes. Future dedicated ice giant missions could provide close-up observations surpassing even Voyager's achievements. These next-generation instruments will reveal atmospheric layers, chemical reactions, and storm dynamics currently beyond human observation capabilities. They may discover entirely new aspects of Neptune's atmospheric behavior. Next-generation space telescopes and dedicated planetary missions will revolutionize understanding of ice giant atmospheric systems. Modern Neptune observations generate enormous amounts of data that exceed human ability to analyze manually. Artificial intelligence and machine learning algorithms can find patterns in these massive datasets that humans would miss. Our systems can automatically detect new storms, track atmospheric features across multiple images, and identify subtle changes in atmospheric circulation patterns. These algorithms work continuously without fatigue and can process years of observations in hours. Machine learning has already discovered new atmospheric phenomena by analyzing archived telescope data. And our algorithms can spot correlations and patterns across decades of observations that reveal long-term atmospheric behavior. Artificial intelligence enables pattern discovery in large-scale astronomical datasets beyond human analytical capabilities.